नहमदुहु व नुसल्ली अला रसूलिहिल करीम अम्मा बाद फ़अऊज़ु बिल्लाहि मिनश शैतानिर रजीम बिस्मिल्लाहिर रहमानिर रहीम। आज का हमारा जो टॉपिक है, एजेंडा है, लेक्चर है, वो 10th क्लास की रीडिंग क्लास पर है। क्योंकि बच्चों को बाज़ का स्पेलिंग ही नहीं पढ़ने आते, वो फिर क्वेश्चन कैसे याद करेंगे। इसीलिए सबसे पहले उनकी रीडिंग का करेक्ट होना सुनिए। इस मैं रोल नंबर 1 को दावत देता हूँ कि वो आकर बाकायदा रीडिंग का आगाज करें। औज़ु बिल्लाहि मिनश शैतानिर रजीम बिस्मिल्लाहिर रहमानिर रहीम। शुरू अल्लाह के नाम से जो बड़ा मेहरबान नहायत रहम करने वाला है। चैप्टर नंबर 9, केमिकल इक्विलिब्रियम। We owe our existence to equilibrium phenomena taking place in atmosphere. We inhale oxygen and exhale carbon dioxide, while plants consume carbon dioxide and release oxygen. This natural process is responsible for the existence of life on the earth. Many environmental systems depend for their existence on the light equilibrium phenomena. For example, concentration of gases in raw water is governed by the principles of equilibrium. The lives of aquatic plant and animals are indirectly related to concentration of dissolved oxygen in water. Reversible reaction and dynamic equilibrium. In this chemical, the substance that combine alkyl reactant, the new substance formed are called product. For example, when H2 and O2 combine, they form H2O product. H2 2H2 plus O2 heat to H2O. Most of the reaction in which the product do not recombine to form reactant are called irreversible reaction. They are supposed to complete and are represented by putting a single arrow between the reactant and product. On the other hand, reaction in which product can recombine to form reactant are called reversible reaction. This reaction never go to complication. They are represented by double arrow between reactant and product. These reaction proceed in both ways. They consist of two reaction, forward and reverse reaction. Forward and reverse reaction so are reverse reaction in which one which can made of proceed in either direction depend upon the condition. Let us discuss the reaction between hydrogen and iodine. Because one of the reactant iodine is purple while the product hydrogen iodine is colorless. Proceeding of the reaction are easily observable on heating hydrogen and iodine. Vapors in a closed flag hydrogen iodine is formed as a result. Purple color of iodine fades as it reacts to from colorless hydrogen iodine as shown in figure. This reaction is called forward reaction. On the other hand, when only hydrogen is heated in a closed flat, purple color appears because of formation of iodine vapors, such as in this case hydrogen iodine act as reactant and produces hydrogen and iodine vapors. This reaction is the reverse end of the above. Therefore, it is called a reverse reaction. When both of these reactions are written together as reversible reaction, they are represented as H2 plus I2 forward reverse reaction to HI. Let us have another example. When calcium oxide and carbon dioxide react, they produce calcium carbonate, CaO plus Ca2, CaCO3. On the other hand, when CaCO3 is heated in an open flame, it decomposes to form calcium oxide and carbon dioxide. CO2 escape out and reaction goes to complication. CaCO3 CaO plus CO2 decomposition. In these two reactions, decomposition in is reversed to combine or vice versa when calcium carbonate is heated in a closed flame so that CO2 cannot escape out as shown in figure. Initially, only decomposition take place on but after a while CO2 started combining with CaO to form. Initially, only decomposition take place on forward, but after a while, CO2 started combining with CaO to form CaCO3. In the beginning, forward reaction is fast and reverse reaction is slow, but eventually the reverse reaction speed up and both reaction go on at the same rate. At this stage, decomposition and combination take place at the same rate, but in opposite direction. As a result, amount of CaCO3, CaO, and CO2 do not change. It is written as CaCO3 forward reverse reaction CaO plus CO2. When we think of term equilibrium, the first word that usually comes to mind is balance. However, the balance may be achieved in a variety of ways. Thus, when the rate of forward reaction is the same as the rate of reverse reaction, the composition of reaction mixture remains constant. It is called chemical equilibrium state. At chemical equilibrium, there are two possibilities. Number one, when reaction causes to proceed, it is called static equilibrium. This happens mostly in physical phenomena. For example, a building remains standing rather than falling down because all forces acting on it are balanced. This is an example of static equilibrium. When reaction does not stop, only the rate of forward and reverse reaction become equal to each other but take place in opposite direction. This is called dynamic equilibrium state. Dynamic means reaction is still containing at dynamic equilibrium state, rate of forward reaction is equal to rate of reverse reaction. In the reverse reaction, dynamic equilibrium is established before the complication of reaction. It is represented. It is represented. It is represented graphically. At inertial state, the rate of forward reaction is very fast and reverse reaction is taking place in negligible rate. But generally, forward reaction slow down and reverse reaction speed up. Eventually, both reaction attain the same rate. It is called dynamic equilibrium state. For example, in case of reaction between hydrogen and iodine, vapors of some of molecules react with each other to give hydrogen ion H2 plus I to 2Hi. At the same time, some of the hydrogen iodine molecules decompose back. Iodine molecules decompose back on hydrogen and iodine to Hi H2 plus I2. In the beginning, as the concentration of reactant is higher than that of product, the rate of forward reaction is forward than the rate of reverse reaction. As the reaction proceeds, the concentration of reactant will gradually decrease while that of product will increase. Consequently, the rate of forward reaction will go on decreasing and the reverse reaction will go on increasing, and ultimately the two rate will become equal to each other. Thus the equilibrium with set up and concentration of various species become constant. It is represented as H2 plus I2 forward reverse to HI. Microscopic characteristics of forward and reverse reaction. Forward reaction, reverse reaction. It is reaction in which reactant react to form product. It is reaction in which product react to produce reactant. It take place from left to right. It take place from right to left. At inertial state, the rate of forward reaction is very fast. In the beginning, the rate of reverse reaction is negligible. It slow down gradually. It speed up gradually. Microscopic characteristics of dynamic equilibrium. An equilibrium is achievable only in a closed system. An equilibrium state, a reaction does not stop. Forward and reverse reaction keep on taking place at the same rate but in opposite direction. At equilibrium state, the amount of reactant and product do not change. Every physical properties like color density etc. remains the same. At equilibrium state is attainable from either side, starting from reactant to form product. At equilibrium state can be disturbed and again achieved under the given condition of concentration, pressure, and temperature. Law of mass action. Goldberg and Vaga in 1869 put forward this law. According to this law, the rate at which a substance reacts is directly proportional to its active mass, and the rate of reaction is directly proportional to the product of its active masses of reacting substance. Generally, an active mass is considered as molar concentration having unit of mole decimeter minus 3 expressed as square brackets. For example, consider a reverse reaction of the type A plus B, KF, C plus D. Suppose A, B, C, and D are the molar concentration, mole decimeter minus series of A, B, C, and D respectively. According to this law, mass action, the rate of forward reaction, ये proportional का साइन है A, B, proportional का साइन खत्म करके K, F, A और B. Similarly, the rate of reverse reaction, proportional का साइन C, D, K, R, proportional का साइन खत्म करके C, D, where KF and KR are the proportionality constant called specific rate constant of forward and reverse reaction respectively. At equilibrium state, the rate of forward reaction is equal to the rate of reverse reaction. KFAB is equal to KRCD. KF over KR is equal to CDAB, where KC is equal to KF over KR. KC is called equilibrium constant. It is represented as Kc is equal to CD over AB. Law of mass action describes the relationship between active masses of the reactant and rate of a reaction. Derivation of the expression for equilibrium constant for general reaction. Let us apply the law of mass action for a general reaction. Small A plus B or B forward verse C plus D or D. This reaction consists of two reactions, forward and reverse reaction. According to this law, the rate of chemical reaction is directly proportional to the product of molar concentration of its reactant rise to the power equal to their number of mole is the balanced chemical equation of the reaction. Let us first discuss the forward reaction A and B and the reactant where A and B are their number of moles. The rate of forward reaction according to this law mass action is Kf proportional का साइन A उसकी पावर A B की पावर B. Kf is equal है Kf A और B, where Kf is the rate constant for the forward reaction. Similarly, the rate of reverse reaction Kf is directly proportional to the product CD, where C and D are the number of moles given in the of C or CD or D, where C balanced chemical equation thus Kr proportional का साइन सी डी के आर इज इक्वल के आर is equal to Kr C or D, where Kr is the rate constant for reverse reaction. We know that at equilibrium state the rate of both end reaction are equal. The rate of forward reaction is equal to the rate of reverse reaction, such as R F is equal to RR, and putting the value KF, RF and RR, KF A, B and KRC ulti. By taking the constant on the side and the variable on other side of equation, the above equation becomes Kf over Kr is equal to CD over AB. Kc is equal has CD over AB. Kc is equal है Kc is equal to Kf over Kr. It's called chemical constant. This expression is for chemical equilibrium constant. All the reversible reaction can be expressed in the form such as when nitrogen react with oxygen to form nitrogen monoxide, the reversible reaction is as follow: N2 plus O2 forwards to NO. The rate of forward reaction Kf is equal to Kf N2O2. K, the rate of reverse reaction RR is equal to KRNO squared. The equilibrium constant expression for this reaction is Kc is equal to NO to NO square N square N to O.